Hey guys, it's Chili here. Welcome back to STD Gems. Today we're looking at what I like to call the generators. So up until now we've been looking at functions that, move things, copy things, transform things. But today we have functions that don't have a source. They don't take any data. They make it out of thin air and they jam it in containers for you. Pretty useful, especially during testing. And it's a very, very simple, very light topic. So first one we're going to look at is fill. And it just copies a single value into a container. Like many of the algorithms, it has a range version and it has an n version. So let's take a look at the n version. It's fairly simple. We'll create a vector here. We're going to reserve some space. And then we're going to fill into that empty vector using the back inserter. I'm going to put 10 items. Value is going to be 69. You run that. Yeah, you get your 69s in your container. Pretty simple, except, of course, you would never do this, right? This is kind of dumb because vector already has a constructor that takes a count and a value, and we could achieve the exact same effect with much less code doing it this way. So, not really good. Fill isn't really that great for filling up empty containers, but if you got an existing container and you want to add some new stuff to the end, then it's pretty useful. You can, let's reserve, then we go std fill in, give him a back inserter, give him the count, give him the value that we want to add to the end of this container. And you run that, works like a charm, it's that easy. And of course you can use the range version to write over existing values in a container. Give it a couple of iterators, give it a value, and it will write over a bunch of values in the middle of the container. Fairly simple. So yeah, that's fill. Pretty basic, but also pretty useful. Now, there's often the case comes up where you don't want to fill a container with a single value. You want to fill a container with an increasing range of values. Let's say you want to fill it with values from 0 to n-1. And the standard library's got your back there as well. We got to scroll down a little bit. We got a little dude here called IOTA, and it fills with sequentially increasing values starting with a certain value. So you can start from 0, you can start from 1, whatever you like.
I would do anything for my girl.
The only real downside to IOTA is it doesn't have an n version, so you've got to have a container that already has elements in it. You can't use the back inserter. So let's say I got a vector v, and I wanted to use std IOTA. Std IO doesn't seem to be in there. Tricked you, because IOTA is a little tricky dude. It's in the algorithm library right here, but the header is numeric, so there you go. Just keeping you on your toes. So we'll put numeric in there, and we got IOTA, and we're gonna go v.begin, v.end. We'll start with 0, as any true programmer would. And there you go, you get your increasing range. Not bad. It's kind of a bummer that you got to create all the elements before you can write in there, but it's still useful. So yeah, fill, IOTA, they're simple, they're useful, they're not very versatile though. Now, the real generator is of course std generate, if I can frickin' find it. Here it is. Generate and generate n. So what these guys do, yeah, you give them an iterator, you give it a count because it's an n boy, and n boys, that's how they roll. You give it a callable thing, a functor or a function, the generator. It will call that and generate values for each element in the range. And that's a beautiful thing. You can give it any custom function and it'll generate stuff for you, anything you want.
Anything for my princess.
Now, one of my favorite ways to use a std generate is with a random number generator. So I can go, std generate n, and then I got to give it my iterator. Say give me 5 values, and my function will just be RNG, because RNG is a callable object. And there you go. You can jam a bunch of random numbers into a container. Works like a charm. Now usually you don't want to just, have the full range of int or whatever for your random numbers. You want to have a distribution. Now the problem with this is you can't just jam D. You can't jam your D into your generate. Why not? Well, because D actually takes a parameter, and the function that generate is expecting takes no parameters. So there's a little bit of a mismatch here. A couple of ways you can handle it. Obviously, you can create a simple lambda here, bind these guys to it, and then call D on your RNG. So this lambda now takes 0 parameters. it fits, and it works like a charm. The other thing you could do if you're feeling a little frisky, you could use STD bind the RNG to the D, and that also works perfectly fine. Now let's say you wanted to do something like IOTA, right? But you don't want to increase by 1, you want to increase by 3 every time. So how would that look? Well, I mean, first of all, you can't use IOTA because IOTA only increases by 1 every time. So that's sort of out of the question. What would it look like? Well, let's use a lambda, and let's create value and set it equal to 0. So this is a variable. It's going to be bound. It's going to be captured, created and captured in this lambda. And what we'll do is we'll store the old value, increase val by 3, and then return the old value. Now the compiler don't like this, and the reason why is because when you have got a variable that is captured, that's created in the lambda like this, it's not an external variable that's being captured. This is being created for the lambda itself. By default, you're not allowed to mutate it. Lambdas by default can't have state, but we want to have state because we want to remember from one invocation to the next what the previous value was, because we want to build upon that. We want a sequence. So in order to do that, it's very simple. Just declare your lambda as mutable, and now you have a stateful lambda. It will remember its value and it will build it up across invocations. And there you go, you've got that increasing sequence. So yeah, stateful lambdas, usually you don't want your lambdas to be stateful, but for this case of generating, it's very useful. All right, now the last guy we're going to look at, it's a little more complicated than the other ones, but it could come in handy. I could see this coming in handy in a games application or otherwise. It's called sample. Select n random elements from a sequence. Now this guy is a little misleading. It doesn't do what I originally thought it would do. I thought you give it a range, a population, and it would select n elements out of that range, just randomly selecting. So if I had a range of 10 elements and I wanted 50, it would just take 50 random elements out of that and put them into the output iterator using the random number generator. That's what I thought, but that's not how it works. Don't get mixed up here. How it actually works, so let me show you. So let's say you give it a population range, you give it a random number engine, you give it an output iterator, you say, give me 4. What it does is it scans through this range and it picks at random 4 of these guys. And you get A, D, F, G, or whatever. So it never picks the same element twice. And another thing that it never does, it always gives you them in the order that they were in the population. And if you give it a number like, let's say, 24, it's not going to keep taking. It'll just give you A, B, C, D, E, F, G, and that's it. It won't give you more than the number of elements that are in the population. So that is basically how it works. And I thought it would be nicer if you had a population you could just take as many as you want, and it would just be perfectly random, but that's not how it works. And yeah, it says it right here. If n is greater than the number of elements in the sequence, selects last minus first elements. So if we select a bunch of random guys from vector A here, you get 3, 4, 6, 8. Try it again, you get 3, 7, 8, 9. It's random, but they're always going to be in order, never going to be duplications. And if you try to select more than is in the population sequence, you're just going to get the entire sequence. So that's how that works. It's a little less useful than I had originally thought when I first saw the function, but I could still see it having a place. That's going to about do it for today. Thanks for watching. Hope you enjoyed the video. If you did, please click the like button. It helps a lot. And I will see you soon with some more STD Gems.